Hello and welcome. My name is Richard Taverner and I'm your host of Any Further Questions. You are listening to episode 13, where today I have Chris Lintott back to discuss his last lecture of his series. Previous episodes of Any Further Questions are available to listen to on Spotify and Apple Podcasts, so please do go and check them out now. For those of you who don't know Chris, he is the current Gresham Professor of Astronomy and host of the BBC's Sky at Night. During the day, you'll find him at the University of Oxford, where he is Professor of Astrophysics. Today, Chris will be answering the unanswered questions from his last lecture, First Light, Revealing the Early Universe. It is available to watch on our YouTube channel, and so for context, it's probably a good idea to go and watch it first before listening to us. Now, you probably may have noticed that there was a lecture before the First Light lecture, which was about aliens. It was called Is It Aliens? The Most Unusual Star in the Galaxy. Chris answered all the questions that were put to him on the day of that lecture, but that doesn't necessarily mean we won't touch on it during our discussion today. Chris, how are you?
I'm all right, thank you. Yeah, it's been a busy few weeks, but
it's good to
relaxing at the end of the Gresham season. And starting to think about next year's lectures, which will surprise people with another time. But yeah, I've got some good plans, I think.
We can possibly, at the end of the podcast, you could possibly say a few things,
sure,
if you can, about your new series, which is beginning in September. So we'll begin with, if the light is millions of years old, how do we know the source is still there? It could all have gone.
Okay, so straight into cosmology. This lecture, I should say, was, I think, hopefully not the hardest to follow, but I felt I was working quite hard because these topics are confusing. And so this is a common question. So I spoke in the lecture about telescopes being time machines, so that we see light coming to us from distances that mean it's travelled for millions or billions of years. And so we get to see the past in this way. When we see a galaxy whose light has been travelling towards us for 10 billion years, we see it as it was 10 billion years ago. And of course, that means that we're not seeing it as it is now. And we're not seeing the universe as it is now. We're reading the past of different bits of the universe. So there's no guarantee that we don't know what that galaxy grew up to be. It's rather like having a photo of somebody as a 5-year-old and no other information, right? Now, I can project that if I have an image of you as a 5-year-old, I can guess that you got taller, that, your hair eventually goes grey, that, I could probably predict that you have a job at some point in your life, because that's what typically happens to 5-year-olds. But I don't see the rest of that story from that one photo. And so that's what we've got. We've got these slices of the universe that we see at different ages. And by assuming that we're seeing the same story in different bits, we can sort of piece it together. Now, that gets us into trouble sometimes. So one example is that we might be particularly interested in the history of galaxies like the Milky Way, like our own galaxy. And you'd be tempted to look back in those James Webb JWST images and say, okay, so those blobs, which we see as they were 10, 12, 13 billion years ago, those are the 5-year-olds that are going to grow up to be the adult Milky Way. But we also know we're seeing the brightest galaxies. We're only seeing the really luminous ones back in the early days. So it may be that our Milky Way had a very obscure childhood, that we haven't yet reached the point that we can see galaxies as puny as our own. We may be seeing only those 5-year-olds that, have learnt to play the violin to grade 8 or stand out in some other way. This analogy is getting a bit baroque, but you sort of get the idea.
Yeah.
So it is true that you have to be careful about which snapshots you match with later snapshots, but the idea is the same. So to first order, we're not seeing things as they are today. We're seeing their past. Then it gets a bit weirder, because when you look as far back as JWST is doing to galaxies as they were 12 or 13 billion years ago, just after the Big Bang, which we think was 13.8 billion years ago, we're looking at a bit of the universe that, in technical language, isn't causally connected with us. And so what that means is, because of the expansion of space that's happened all the time that light's been coming towards us, if we were to send a message back to that galaxy now to say, hey, we saw you, well done, or whatever else you want to communicate to whoever's now living in this blob, that message would never get there, because the expansion of space has pulled the galaxies apart, so no light could travel now from that galaxy to us or from us to that galaxy. So we will never see that galaxy as it, even if you lived forever, you would never see that galaxy as it was 13.8 billion years after the Big Bang. So that's quite, and I don't know what to do with that fact. It's quite odd that we're seeing bits of the universe that we're now disconnected from, but that's what the maths tells us. That's what the expansion has done.
And how do we know the light is constant throughout that universe rather than just our local area? Does the discrepancies in the Hubble tension observations hint this?
So there are theories. I guess the question means, do we know the speed of light is constant?
Yeah.
Because I'm using that as a yardstick, right? And so, that's what allows us to tell this story. There are a set of cosmology theories which tend to be known as tired light theories, where the speed of light changes over time, and you can perhaps explain some aspects of what we're seeing. And I would be sure that someone somewhere has a theory where you can explain this discrepancy in the Hubble constant, this expansion, by changing the speed of light. But that's a big claim. Relativity is based on the idea that the speed of light is constant. Almost all of modern cosmological physics assumes that it's the same. So I would want very good evidence that the current theory doesn't work before we throw out that foundation stone. We have some measurements of... I think you can get some sort of indirect evidence that things work, that the speed of light is constant, because we know that other constants are the same. When we look at the spectrum of a galaxy, we see lines left by different elements, and they depend on some very fundamental constants of nature, not on the speed of light, but on things like the fine structure constant, which happens to be a number that we call alpha. The fine structure constant, we think, is the same to within a few percent in the early universe as it is today, because those spectral lines are in the same pattern in the same place. So you don't just need... If you want the speed of light to change, you have to explain why it changes and the other fundamental constants of the universe don't.
Right.
Okay? In your theory, there can be something special about light, but I'm not convinced that's a good answer yet. I think there are other explanations, like not understanding star formation or supernovae, or even the history of the expansion itself, that I'd reach to before I let you get away with changing the speed of light.
Our next question was about that expansion and whether that acceleration rate is increasing or not.
Yeah, this is a good question, and which we didn't really have time to talk about in the lecture. So when we talk about the expansion of the universe, we talk often about this Hubble constant, which measures the rate of the expansion today.
Yeah.
And I hope I managed in the lecture to say today, because that's often missed out. People will tell you that this Hubble constant is the rate of expansion, which suggests that it's constant over time. But actually, this has been changing over the course of history. So we can ignore for now, there was a period, we think, right at the beginning of the universe, a period called inflation, where there was very, very rapid expansion. That's a theory, but it explains some features of the universe that we see today. After that, the universe was expanding and it slowed down. And it makes sense that it was slowing down because the only force that acts on large scales is gravity. And gravity is an attractive force. So if you have matter in the universe, and it's expanding, then there should be a drag, and that should slow down. And the more matter you have, the faster that slowdown happens. So this was the idea that gave rise to things like the Gnab-Nib, the opposite of the Big Bang, the Big Crunch that we talked about in the lecture, where you have an expansion that reverses itself. If you have enough stuff, you come back to a contracting universe, and then you can have this nice rebounding universe, which gets you out of ever explaining how it started. But we can measure this process. We can measure it by looking at different snapshots and measuring the speed of expansion at different times in the universe's history. And when people did that in the late 90s for the first time with accuracy, they discovered that there is this period of slowing down, but something like 2 or 3 billion years ago, things changed and the universe started to speed up its expansion. It's actually accelerating today. And we don't know why that is. We give the phenomenon... So it has to be a force. One way of thinking about it is that it has to be a force that acts on large scales, but it can't be gravity because gravity pulls things together. And so we give that force the confusing name dark energy. I don't know what it means for energy to be dark. It's not really energy, although I guess that's equivalent to a force. Yep. And that's the dominant feature of the universe today, but we've no idea why that's happening, and our theorists are pretty confused about it.
So that then... I have a question about gravity. Where did gravity come from? And does gravity just come from the fact that there's a lot of stuff in the universe? And is it related to that? Or
yeah, so gravity comes from mass.
Yeah.
So, or more broadly from energy.
Right.
So the way this works in relativity is that if you have mass, that's a form of energy, and that expresses itself by distorting space-time in the theory, but you can think of it as space. So this is where normally as a physicist we start to rock out analogies involving rubber sheets and bent space-time and so on, none of which are hugely convincing. But so if you just take the solar system, I think you have the sun in the center, you've got the Earth in orbit. So then you must have a force that's acting on the Earth because Newton's laws tell us that the Earth would just go in a straight line if it wasn't being acted on by a force. And we don't go in a straight line. We're pulled into a near-circular orbit around the sun. So there must be a force that's acting on us, and that force is gravity. So one possibility, in fact, one way of thinking about this is to have particles, gravitons, exchanged between the sun and the Earth. So the sun would send out its gravitons, they interact with the Earth, and that somehow tells us how to move. But a more natural explanation in relativity is that by plonking the sun there, we bent space around the Earth, and so that it rolls around in this bent space so that the circle becomes the lowest energy solution. So big things bend space, and that's what we experience as gravity. And so if you drop something where the Earth is, but without the momentum, it will fall down towards the sun because it will roll down this bent space.
So has that led to the confusion because we shouldn't really be accelerating back up because there's been more mass? So really we should be slowing
so on
down.
Large scales, mass impedes the expansion because it's like you're trying to stretch. If you think of the expansion as space being stretched, if I put a giant marble or something in there, then that's harder, right? So the more stuff you have, the slower the expansion should be over time, even if it's got some initial impetus. But we're seeing this speeding up. So most people would say it's a property, therefore, of space itself. And that explains why it's become important lately, because we've got more space. As the expansion is being continuing, we literally have more space in the universe. And so if this acceleration is a property of space, it should show up at late times.
Or we could be losing things.
We could be losing things. There's some theory that gravity may be leaking into other dimensions or something like that. But if we just stick to our...
what we know.
And we don't see the mass of the universe changing. So we have other ways of measuring mass, like counting the number of galaxies that we see. So it's not that mass is going missing. In fact, there's good reason to believe mass is conserved. So we have this extra force that seems to be a property of space, but we don't have any understanding of space that lets us calculate what this force should be.
Yeah.
There are in quantum physics, there are ways to think about space that produce something that looks like this accelerating force, but in the theories, it's billions and billions and billions and billions and billions of times stronger than the force that we see. Okay. So the best guess from quantum physics is that such a force should exist, but it should have ripped the universe apart in its first few seconds. And we know that didn't happen because we're sitting here. So we're basically stuck on dark energy. What we can do, and lots of work is being done, is to try and measure the rate of change of that acceleration. So everything we know at the minute says it's a constant acceleration per unit space. But if we could find that it wasn't that there was some dependence, that would give us some clue to the physics. And so there are big projects like the European Space Agency's Euclid spacecraft that's up there now observing the distant universe to try and pin this down. My own Vera Rubin Observatory project that I'm involved in, that I've mentioned many times during the course of these lectures and podcasts, which is going to scan the whole sky from Chile. Part of the point of those projects is to measure this parameter, see how the acceleration is changing.
Right. And so on dark energy, you alluded to the fact that, so we had a question, back to the listeners' questions, we had a question about what role does dark energy or dark matter play in the early universe? Is that the role it only plays, just explains the unexplainable?
Well, interesting. So dark energy, which is the label that we put on this accelerating force, as I've said, becomes important later.
Right.
So if we're trying to explain the first few billion years of the universe's history, you could take dark energy out and not worry too much. Okay. I don't think you'd see much difference. Dark matter makes a big difference because of the fluctuations that we see in the microwave background. These spots that I said were the seeds of galaxies. So if you create a universe in a computer that has more matter, It's a lumpier universe.
Okay.
And so if you take dark matter out, if you build a universe with only the matter that we know is made of stuff that we understand, like protons and neutrons and hydrogen and helium and so on, then you get a much smoother universe. And so galaxies take much longer to form. And so you don't do such a good job of producing a universe that matches the one that we see today. So dark energy is a later phenomenon. You can worry about that for the last few billion years. But dark matter, you need to get the recipe for the early universe needs dark matter to close the gap between what we see and what the microwave background tells us should be there.
And the word dark just refers to something that we don't know.
In terms of dark energy, it's sort of by analogy. For dark matter, it's got a more technical meaning, which it means doesn't interact with light.
Okay.
So we know that this isn't matter that we should see shining or whatever, which sounds kind of mysterious, but that it's really just a statement that these are probably, if these are particles, they're neutral particles. So a neutron won't interact with light either. Light likes to interact with charged things. Yeah. So maybe dark matter is not that mysterious, but we haven't pinned down which particle it is or where that's formed or why it's formed or why it dominates. There's something slightly suspicious about the fact that we think there's about 6 or 7 times as much dark matter as normal matter. And I don't know, there's a physicist's intuition maybe that that's a weird number. Like we're used to either processes that produce equal amounts of things if it's the same process, or if it's a runaway process, we should have all dark matter or all normal matter with a sprinkling of these other rare stuff. So I don't know, there's something funny to me about the fact that it's 6 or 7. Like that feels like that's being calibrated, right? That feels like a recipe. Yeah. So I feel like I want an explanation for why that's the number, but we don't know what that is.
Right. About galaxies, how do you know that the galaxies are made of certain elements?
Yeah, this is, I think, one of the great triumphs of astrophysics. In fact, you can argue it's the thing that turned astronomy, sort of mapping the sky, into astrophysics, trying to understand the objects. So this is the great discovery from the late 19th century that if you take light from a star and you split it up through a prism or a grating, so you get a rainbow, you see a fingerprint of all the different elements. So different elements have characteristic wavelengths. So sodium glows brightly in the orange. Hydrogen has a set of lines in the red at very particular frequencies, which reflect, it's to do with the structure of the atoms, actually. It's the position of the electrons around the atomic nucleus, which is different for different elements. So we see those fingerprints in stars, and so that's how people realised that the sun was made mostly of hydrogen with a sprinkling of other elements, how helium was discovered. We see that other stars are made of the same stuff as the sun, so that was the proof that they were indeed just suns. And then as telescopes got bigger, we've been able to do this with galaxies. And often we're looking at the starlight, and we can play this game, but we can also see light from gas in the galaxies, particularly in radio wavelengths. So, for example, there's a very famous amongst astronomers line at a wavelength of 21 centimeters, which is where neutral hydrogen emits light. And so that's a radio wavelength. You can tune Jodrell Bank to that. Yeah. We see that wavelength in other galaxies as well, and that's where the hydrogen and helium comes from. In case of the galaxy I talked about having primordial gas, mostly hydrogen and helium early on, that's infrared radiation. So the same game, JWST, this marvellous space telescope, which you all know about because you've seen the images that I've shown and that many others have shown in the media, mostly is built to do spectroscopy, to measure the spectra of these distant things and get this sort of information. So I think I was just at their Space Telescope Mission Control in Baltimore a few weeks ago, just after the Gresham lecture, in fact, and they were saying about 75% of its time, about 3/4 of its time is being used for spectroscopy because we want to know not just what things look like, but what they're made of. And so this is the key.
About that's a good spectroscopy. Are there any model-independent observations in cosmology beyond spectroscopy?
I'd have to think about what you mean by model independent. So often, so in cosmology, when we do spectra, we see the same pattern, but they're shifted. Yeah. For these galaxies, that's the redshift. That's how we measure the expansion. How you interpret that, I'm not sure what model independent means. What we measure in all of these things is we're trying to, as I've made the point in many of my lectures this year, we're trying to make simple measurements. So redshift is something we can measure. We can measure brightness of a thing. We can measure how that brightness changes over time if it's something like a supernova. Sometimes we do things like we can measure the size of a galaxy or the size of an object. So one way to get a distance to a galaxy is that it only works for nearby galaxies, but we know that when a sun-like star dies, that it goes through a phase where there's a planetary nebula, often a ring-shaped structure made of the outer layers at the start. They're beautiful objects, but they're also all almost always the same size, roughly. So if you see one in a distant galaxy, you know what size that should be in reality, comparing to ones in our galaxy, and so you can use that to get a distance, like you could work out, I don't know, how near a football was based on how big it appeared as it headed towards your head.
Yeah.
Strange analogies today, but fine. So we can make all of those measurements, and then we need a model that explains them. So the trick is to keep the model as simple as possible. So the model that works is this expanding universe. And then you put into that, I'd be calling it a recipe, how much dark matter there is, how much dark energy there is, what time it is past the Big Bang, and you check to see if these observations are consistent. And mostly they are, with the exception that we need to add this dark energy thing. Without that, it doesn't work very well. And there's this Hubble tension, so that when we play this game, if you ask the people who look at the microwave background versus the people who study nearby objects and try and infer the cosmological model, really, the Hubble tension is a statement that they slightly disagree about which model should be favoured, and that's why theorists are excited, right? Because they would all want to bring in a more complicated, spectacular model with, I don't know, the Lintott particle or Lintott anti-gravity or whatever you want to call it, that is this magic extra ingredient that explains this stuff. But we almost never get a model-free observation because you have to think about distance to understand the brightness, and so it's about whether your model is consistent.
We had two questions on Z11.
One of the distant galaxies.
One of the distant galaxies. Yeah. Why is Z11 yellower than the other galaxy? And they put the redder galaxy in the image.
Yeah.
If Z11 is further away.
I'm glad people have been looking at the blobs in these images. So you have to worry about two sets of things. So one is so the colour of a galaxy is influenced by two things. So one is its redshift. So I take the same galaxy, put it in the distant universe, it'll be more redshifted. But we also have to worry about which stars have formed. So if we assume that when you form stars, you form all types of stars. You form red dwarfs, you form yellow dwarfs like the Sun, and you form the big blue OB stars, the most massive stars, then star formation changes the colour of a galaxy.
Right.
But then over time what happens is the more massive stars burn through their fuel fast. Even though they've got more of it, they burn through their fuel faster and they explode first. So if I just form all my stars in a galaxy once, I get quite a blue galaxy because we see all the light from these massive luminous stars. But then within the course of about 1 million or 10 million years, they will die and the galaxy will shift towards being redder. And so the colour of the galaxy tells you about the redshift, but it also tells you about when and where star formation happened. And these galaxies have extreme star formation histories as well. So we have to look at the spectra to find the lines that give us the redshift, and then we can infer what the stellar population is. So it's not just a case of looking for the reddest blobs and declaring that you've discovered the most distant galaxies, though that's a good start.
So blue means it's younger and red means it's older?
Young populations of stars include the blue massive ones because they die off first. Astronomers are confused about this stuff because we believe that the most massive stars are the hottest and most luminous and they're blue. So in all astronomy, blue is hot and red is cold, which is confusing. But for a galaxy, actually, if you ever look at, think about a Hubble picture of a beautiful spiral galaxy, what you'll see is that the spiral arms are picked out in blue. And that's because those are places where star formation is happening in the last 1 million or so years. And so we get these bright, massive blue stars that then die off. Whereas if you form a red dwarf if in the image that we're seeing a population of red dwarf stars is forming, then they are almost certainly still there today.
Okay.
So if you could transport yourself back to that galaxy, then you'd be able to go and find the stars that formed. The oldest stars in the Milky Way are 12, 13 billion years old.
How can you tell that Z11 is made of helium?
So that's from the spectrum as well.
Right.
So again, this is the great magic of all of this stuff is that we can check that it has helium. It has hydrogen as well, but it's this primordial.
That's the made up of the elements. It's it's the colour of it.
That's right.
Tells you.
Yeah. Either there's two ways. Either it depends on the temperature of what's shining. So if you have something like hot gas, then you see emission at that colour. So that's why old-fashioned sodium streetlights used to glow orange, because it's the sodium itself glowing. The other way that this comes out is if you have a background light source, like a star or something, and the light goes through the gas, then you see a black line. In the sun, they're called Fraunhofer lines, where you lose energy because it gets absorbed by that element. So sometimes they're absorption, sometimes they're emission, but the principle is look for the pattern at particular wavelengths.
We had a very technical question, but maybe what you've just said might allow us to understand it a bit better. Are the spectroscopic redshifts, as per the Z11 galaxy, frequency dependent through dispersion via curvature or interstellar dust?
Yeah, so people have spent a lot of time trying to explain away redshifts. Right, because that's the foundation of this. That we have other evidence, but it's the foundation of this model of an expanding universe, which is, whatever else we think about it, counterintuitive. And particularly, I remember when I was watching as a student, when the evidence for this acceleration, this dark energy came out, people said, well, look, fundamentally, the evidence for dark energy is that we're seeing supernovae that are fainter than they should be. Therefore, we're assuming they're further away than we thought they were. But maybe there's some dust, some small particles in the way that absorbs the light, and maybe that would explain things. But dust has a particular color profile. So when we say dust, we're talking about particles the size of sand grains made of carbon or perhaps silicon or something like that. And it tends to absorb red light more than blue.
Okay.
And so you should see, if I take a galaxy and its shift has been caused by dust, it should be non-uniform. The bluer light should shift less than the redder one, and we don't see that. We see a consistent shift. So you can, of course, invent very magical dust. So in the literature for a while, people were playing around with models of what they call grey dust, which is dust that magically affected all wavelengths the same, and you can sort of play around with that. So, but that gets you into complicated trouble with things like observing the microwave background, which also we see travelling through the galaxy and would be affected by dust. In fact, the people who study the microwave background spend a lot of time extracting the effect of dust in our galaxy. So I don't think it can be dust. I think these redshifts, where we've got a spectrum, I think the redshifts are real.
Yeah.
And the easiest way to explain that is the expansion of space. But I don't think, much as astronomers love to blame everything on dust, I don't think we can use that to get out of the hole here.
We had two questions on the cosmic microwave background. Is the cosmic microwave background increasing in redshift over time due to expansion? Will there be a point that it can't redshift anymore and stays at one set frequency?
So we don't think so. So it is changing. So as the universe expands, the light that's travelling towards us from the cosmic microwave background shifts to longer wavelengths. So it too experiences a wavelength. In fact, it was emitted probably just in the infrared. So at the time when it was emitted, it would be a bright infrared background, and it's faded over time because of the expansion, which redshifts its light. So it will get fainter and fainter and fainter and move to longer and longer wavelengths. But we don't think there's a limit to that process. As long as the universe is expanding, it should continue to fade away. In fact, if you were science fiction wise, if you were transported to a new universe, one of the ways you could realise that you were in a different universe would be to measure the wavelengths at where the CMB peaks. And if that was different, you'd know you were in either a different time or a different universe altogether. So a handy tip for all you universe hopping travellers out there.
Yeah. Is there any way we'll be able to know why the microwave background is uneven? Or will it always be beyond what we can observe?
Well, you should never say that anything's beyond what we can observe. I think part of the point of the question is that if we can't get light from before the CMB, then how could we infer anything before it? There's some hope that maybe particles could travel to us from a time before the microwave background. So we may have a neutrino background, a background of light particles that some telescopes are looking for. But actually, there's a nice idea, which goes back to this idea I touched on a minute ago, which is the idea that there was this very rapid expansion called inflation in the first tiny fraction of a second of the universe. Now, we know that on a very small scale, space is lumpy in some quantum sense, that it has a property where there are particles appearing and disappearing all the time. It's sort of this magical stage where things can happen. But that's all on the quantum scale. Now, if I suddenly increase that by a factor of billions and billions and billions, what were quantum fluctuations, places where a particle had just appeared or just disappeared, become things on galaxy scales. And so it may be that what we're seeing in the microwave background is the result of quantum processes blown up. It's like suddenly looking through a microscope and then freezing that image as a poster on the wall or something like that. So that seems convincing to me. What's nice is that there's some prediction about how that would happen at different scales. So how many big blobs you'd have versus small ones. And people have looked to see if we can prove that epoch of inflation happened. There was a result announced 10 years ago now, nearly, by a team called BICEP, who were studying the microwave background, who thought they'd seen in their pattern of blobs evidence for this inflationary epoch. And there are other teams tracing this. It turns out the BICEP team were wrong. They hadn't correctly subtracted the effect of dust in our galaxy, and it was a bit of a scandal in that they thought they were going to win the Nobel Prize, and almost immediately after their big announcement, it was clear to almost everyone that they got it wrong. It was just a mistake, right? They hadn't consulted an expert in the dust models because they thought they were secretly competing with others. So, but there are new experiments. We just had a group from the Simons Observatory, which is being built in Chile, with this aim in mind here in Oxford, and they're ramping up. So maybe we'll be able to pin that down through looking at the pattern of blobs might give us a clue.
And lastly, on the redshift, if redshift isn't due to the Doppler effect, how does it come about?
Yeah, I mentioned this in passing. So this is almost everyone, if you read a book or go and see a lecture on this stuff, will make the analogy that if you stand on a street corner and an ambulance is coming towards you with a siren on, then you hear a change in pitch of the siren as the ambulance goes past you. And the explanation for that's kind of interesting. It's quite fun. It's that sound waves are propagating out from the siren, and if the ambulance is coming towards you, then they're compressed because the ambulance is sort of catching up with each successive sine wave. And then as it goes past you, they're stretched out because you have the movement of the ambulance as well. And how much of a shift there is will depend on the speed of the ambulance. So it's the same principle. And
sound is slow.
Sound is slow, right? Yeah. So whether an ambulance is moving at 50 or 70 makes a difference. In fact, this is the principle by a lot of speed traps.
Yeah.
So they bounce something off your car and they look at the change in frequency, and that tells you the speed. Now, light is much faster, so we don't notice the ambulance changing colour.
Yeah.
But in theory, we should do, right? If you measured very sensitively. I don't know if anyone's actually done this experiment. You could probably do this. If you put a patch of something where you knew the colour on the front of a car and then went past very fast, you should see it shift.
Okay.
There's a famous, not very funny astronomer's bumper sticker that has a blue sticker and says, "If you can see this, you're approaching too fast." Astronomer humour for you. Yeah. But all provided for free here at the Any Other Questions podcast. But I've now thrown myself. Oh yeah. So that's a nice analogy for what's happening with redshift. But there are things about it that I don't like because it implies the galaxies are moving relative to us, whereas, as I've said in the lecture, it's space that's stretching. So I think it's slightly misleading to use this Doppler effect analogy. I mean, the nice thing about it is that it tells you that the wavelength depends on the situation of the observer and the thing that's emitting it. But it's not a precise analogy for what's going on cosmologically. I want people to think about space stretching because then the cosmology, I think, becomes a bit more intuitive. Yeah. So I try not to lean too heavily on the Doppler effect, though. As we saw in the lecture, it's almost impossible not to mention it because the habit's there and so on. There are other redshifts, of course. So, of course, I don't know why I said of course, but there are other. Whether you're in a gravitational well affects your redshift as well. So if I fire a laser beam near to the sun and then observe it on the other side of the solar system, it will be changed by having passed near the sun. So there are also other effects that we have to worry about. but so it's not as simple as the Doppler effect, but same principle in that your observed wavelength is changing.
Yeah. Are there any common misconceptions about the Big Bang or the early universe you'd like to address?
Oh, I don't know about the one I think I got this question, which I hate, which is about whether there's an edge to the universe. Because if you get to the point where you're imagining that the universe is expanding, it seems obvious that it's expanding out into something. And, science communication's two favourite analogies are you put dots on a balloon and then you blow the balloon up and the dots get further apart from each other, but that's fine, but there's an outside to the balloon. Yeah. Or if you have raisins in a cake or bread that's expanding in the oven, the raisins get further apart, but of course there's an outside to the bread. And the reason I say I'm not sure I want to address it is, as I said in the lecture, I'm not sure I've got a good answer as to how to think about that. One answer is that the universe is infinite, but that doesn't help you particularly because I can't visualize an infinite loaf of bread, really.
Yeah,
I could try, but I don't have an intuition for that either. And if it's non-infinite, you do have this problem of there being an outside. What we think is true is that if you travelled through the universe, you wouldn't hit an edge. There's no brick wall. There's no point where you reach the end and you've stopped.
Right.
But I don't have a good way of intuitively explaining that.
How do you know that you wouldn't hit a wall?
Well, we don't see any signs
of
that. For example, the CMB is there and around us. So we know that there's at least the bubble the size of the observable universe. And there are good reasons that there are that should be a tiny proportion of the whole. But you're right. Can I disprove the existence of an actual edge to the universe? I don't think I can if it's beyond. I mean, there could be a stop sign, just beyond the CMB, but it's very hard to visualize this stuff. The other one that I think is interesting is that I'm not sure whether you got any questions on this, but people get into a tangle because I hopefully have been very careful to say that we're seeing these distant galaxies as they were 13 billion years ago. What I haven't said is that they're 13 billion light years away because the light's been traveling towards us for 13 billion years, but the universe has been expanding all that time. And so if you say, how distant is that galaxy now, by which you mean something like freezing the expansion and then putting a ruler out, the answer is about 40 billion light years.
Right.
And that freaks people out because people have learned that nothing can travel faster than the speed of light, and it feels like we've cheated here.
And that alludes to our first question about could it have all have gone already?
Right, exactly. Yeah. But the truth is space doesn't have this speed limit. So because it's space expanding, it can expand at whatever speed it wants.
Yeah.
Like light is traveling through space, so space can do what it likes. And I think it's interesting that people react to that. Like I did too. Like somehow people feel like the one thing they know about modern physics is that nothing can travel faster than the speed of light. We've all learnt that. It explains black holes. We're happy with that. And it turns out the rule we've learned is slightly wrong. It's nothing can travel through space faster than the speed of light.
Yes.
But it's somehow become a sort of common sense thing in people's heads, and it's quite difficult to dislodge that.
It's almost like, it reminds me of the fact that if the sun died, we wouldn't know about it for
8 minutes.
8 minutes.
That's right.
And it's like that, but on a larger scale. So if the universe died...
So there's an interesting question, which was in some of the YouTube comments I was looking at, which is... So if the sun disappeared, not just died, but if we just got rid of the sun now, we wouldn't know because of the light for 8 minutes. But you can ask the question, when would Earth's orbit change? And we think the answer is 8 minutes. We think that gravity travels at the speed of light as well.
Okay.
So because it's causing changes in space-time, which have to propagate outwards. And so I think the Earth would continue in its orbit for 8 minutes, and then we'd careen off into the new darkness. But
what about the climate? So does heat travel through the... Heat travels in the light.
Well, don't forget the Earth's heated by light.
Okay,
so it's heated by the sun's light rays.
Okay.
So
the climate wouldn't change either.
No, we've got 8 minutes. Great. So if I have stopped the sun and you're listening, we're now 7 minutes in. So you have 7 more minutes before we're plunged into eternal darkness.
What a horrible thought. Okay.
Yeah, hopefully that won't happen. Of course, if you're listening to this, it's already happened.
It already happened.
Yeah.
You mentioned the great attractor briefly earlier. This is a question alluding to the lecture. Maybe you could remind us what the great attractor is.
So I was going pretty quickly at this point, so I'm glad somebody asked. So when you observe the microwave background, the first thing you see if you map it, well, the first thing you see if you use the equipment that Penzias and Wilson did is you see that it's very uniform.
Yeah.
Then you get better at it. You start to measure small differences in temperature on the sky. And the first thing you see is what's called a dipole. So half the sky looks slightly warmer than the other half. And it feels like this should be telling you something profound about the universe, but it's not. It's our old friend redshift again. Because what's happening, of course, is that we're not on a static place. So we're on the Earth. The Earth is orbiting the Sun. The Sun is orbiting the centre of the galaxy. And our galaxy is moving through space. So that all of that adds up to the fact that there's a direction we're travelling in, on average, in the sky. And that's the dipole. So the direction we're travelling in, we slightly blue shift the cosmic microwave background because we're approaching. This is like the Doppler effect. The direction we're travelling away from, we get this red shift.
Yeah.
So that's what you see on the sky. But then you can ask the question, well, what direction are we going in and why? And so you take out, we understand the Earth's orbit around the Sun, we understand the Sun's orbit around the galaxy, and then you're left with how the galaxy is moving relative to nearby galaxies. And we discover that it's part of this local group, which also has Andromeda and the Triangulum galaxy as big members. And that whole group is moving towards the Virgo cluster. So we're falling into our nearest cluster. But then that whole cluster is moving in the sky towards something that we call the Great Attractor, which is a great name. It's for once, it's really good branding. And the frustrating thing...
It's like something out of Marvel, isn't it?
It's good, isn't it? Yeah. It's like you could save up and buy... I think it's like, the things they used to advertise in the back of comics.
Yeah, yeah.
Send 99p for the Great Attractor, and it'll turn out to be a cardboard model of a black hole or something rather than the actual black hole. That sort of thing.
Yeah.
Anyway... the frustrating thing is, if you're looking at this time of year and you're in the northern hemisphere, look south, you see the constellation of Sagittarius from a dark sky, which looks like a teapot. The Great Attractor is basically there. So that's the direction on the sky we're moving. It's hugely frustrating because it's behind the centre of our Milky Way.
Right.
And so we can't see that part of the sky. It's called... There are obviously some astronomers out there who can name things. It's in what's called the zone of avoidance. Right. Which is also a Marvel thing, I think it should be. So the zone of avoidance is the bit of the sky where we can't see the distant galaxies because our galaxy gets in the way. Yeah. And so we know we're moving that direction. It's almost certainly a huge galaxy cluster. Yeah. But it could be Zong the Merciless with a magnet. Who knows?
So the Earth is moving with the Sun, with our galaxy, in a certain direction. 13.8 billion years ago, we were in a different...
part of the universe.
Universe.
That's right.
Is there any kind of theory as to when we were there? Are we going to see a change in atmosphere?
So the Earth is just an observer here, but what we do see, so this is where computer simulations do a really good job. So we have these supercomputer simulations that show the evolution of the universe, and what they see is that it's the effect of exaggerating those tiny differences we see in the microwave background. So things tend to fall into denser bits of the universe because that's where gravity is strongest and is attracting them. So over time, there's a tendency to end up in a denser gravitational neighbourhood. So we started off in a less dense region. We will have ended up in our little local group. That local group will end up merging with a bigger cluster, and so we'll end up living in the big city. Right. It's the reverse of humans who tend to start in the city and move out as they get older, whereas galaxies become more social over time. Yeah. So on average, we'll end up in a denser environment. But the space is big. The gap between galaxies, even in a galaxy cluster, is large. And so if all you care about is conditions on the Earth, then we won't, unless you're an astronomer, you won't notice any change.
Wow. We've got another question, possibly our last question, actually. What new technology or theory would we need to further develop our understanding of the beginnings of the universe?
Oh, this is a really good question. So I think... we've got these deep surveys like the Vera Rubin Observatory that will tell us whether dark energy is changing. So for cosmology, it's that. But the question is about the beginning. And so I think one of the things that would be really exciting is some of the future generations of gravitational wave experiments where we're looking directly at ripples in space. At the minute, we detect them when black holes collide. But we think there should be some leftover ripples sloshing through the universe from the time where the CMB was established. Right. And they're at a much longer wavelength than anything we're sensitive to now. But we should be able to detect that with experiments that we're building, like LISA, which is 3 spacecraft thousands of kilometres apart. They're going to fire lasers between them and keep an eye out for these cosmic ripples. So finding the gravitational wave background would tell us, it would be like finding another early snapshot.
Yeah.
We'd get a picture perhaps of the 3-year-old universe rather than the 5-year-old. And so that would tell us a huge amount. And that's going to be very exciting.
I'm going to finish with quite a fun question we got in, and I think this came in during the aliens lecture, but it is a question which could have come in from any of your lectures. It says, my favourite name for a telescope which is used for finding exoplanets is the KELT, the Kilo Degree Extremely Little Telescope.
Oh, yes. Yeah, that's right, because you want a wide field of view, so you keep an eye on many stars at once. Yeah, KELT's great.
And they ask, what's your favourite name?
Oh, this is easy. A runner-up place on a similar theme is the Very Small Array, which was a cosmic microwave background experiment.
Yeah.
But the best is there's a Canadian satellite that had a very small camera on board for star tracking, which is what satellites do to keep track of where they are and where they're pointing. But the satellite's long retired, so they're using this telescope to keep an eye on variable stars, and it's called the Hubble Space Telescope. So the Americans have Hubble, Canadians have got the Hubble Space Telescope. And there's just something lovely about that.
Yeah, it's so obvious naming. It's great.
Very Canadian somehow as well. It's nice.
Right, that's all of our questions. So thank you very much for joining me today, Chris, and thank you at home for listening and for all of your questions. Please do keep sending them in when Chris starts his series in the new year. In September, actually, in this year. Chris will be back for his second series as Gresham Professor of Astronomy in September. Is there anything you can tell us about it now?
I almost definitely can't, because we're looking at the observatories and spacecraft that make the discoveries that we covered this year. And we're going to try and do as up to the minute as possible. So I'm particularly excited about a lecture on the Lucy spacecraft, which is on its way to visit asteroids in Jupiter's orbit. It flies past an asteroid which is called Donald Johnson in, I think, March next year. And 2 days after that flyby, I will give a lecture that tells you everything we know about that asteroid, which currently is very little.
Yes.
So it'll drive you lot mad, because it'll be last minute, but
this is the
do
thing.
Cutting edge science.
I host this podcast, but I also am a member of the audiovisual team at Gresham, so I organise all the lectures and how the audio and the visual is done for that, and Chris has given me a few ideas on how we're going to do that for the new year, and it all sounds really great and really exciting. So if you can come to any of his lectures, then please do, because we're going to be doing some fantastic stuff on stage.
Yeah, I won't be quite as exciting as getting an analogue TV out, which I much enjoyed for the CMB lecture.
If you want to be kept informed on our new programme starting in September, then please visit our website, www.gresham.ac.uk, where you can sign up to our newsletter. Chris, thank you again.
Thanks. It's lovely to be here.